Now that we've gotten a grasp on the basics of probability, let's dive into some of the rules of probability. If there's one thing you need to remember for probability, it's these two words. If you see or, you will add probabilities. If you see the word and, it means you will multiply probabilities. If we are certain about the outcome of an event, we will assign the event a probability of 0 or 1, where probability of EI equals 0 indicates the event EI will not occur, and probability of EI equals 1 means EI will definitely occur. If we are uncertain about the result of an experiment, we measure this uncertainty by assigning a probability between 0 and 1. Probability rule 1 shows that the probability of an event occurring is always between 0 and 1. All possible outcomes associated with an experiment form the sample space. Therefore, the sum of the probabilities of all possible outcomes is 1, as shown by probability rule 2. If a single event is composed of two or more individual outcomes, then the probability of an event is found by summing the probabilities of the individual outcomes. Closely connected with probability rules 1 and 2 is the complement of an event. The complement of event E is represented by E. That is, the probability of the complement of event E is 1 minus the probability of event E. The key word in knowing when to use Rule 4 is OR. The word OR indicates addition. This figure is a Venn diagram that illustrates the application of the addition rule for any two events. Notice that the probabilities of the outcomes in the overlap between the two events, E1 and E2, are double counted when the probabilities of the outcomes in E1 are added to those of E2. Thus, the probabilities of the outcomes in the overlap, which is E1 and E2, needs to be subtracted to avoid the double counting. If we are interested in finding the probability of drawing a red card or an ace, we would add the probability of drawing a red card with the probability of drawing an ace, then subtract the probability of drawing a red card and an ace. We indicated previously that when two events are mutually exclusive, both events cannot occur at the same time. Thus, for mutually exclusive events, probability of E1 and E2 equals 0. Therefore, when you're dealing with mutually exclusive events, the addition rule assumes a different form. In dealing with probabilities, you will often need to determine the chances of two or more events occurring either at the same time or in succession. Situations such as this refer to the probability concept known as conditional probability. This is the probability that an event will occur given that some other event has already happened. Probability rule 6 offers a general rule for conditional probability. The notation reads probability of event 1 given event 2 has occurred. Thus, the probability of one event is conditional upon the second event having occurred. Rule 6 uses a joint probability of E1 and E2 and a marginal probability, P, of E2 to calculate the conditional probability P E1 given E2. Note that to find the conditional probability, we find the ratio of how frequently E1 occurs to the total number of observations, given that we restrict our observations to only those cases in which E2 has occurred. Suppose we have an example in which we would like to determine the probability that a car will have a CD player given it has AC. In this instance, we would take the probability of a CD and AC divided by the total probability of AC. We previously discussed that two events are independent if the occurrence of one event has no bearing on the probability that the second event occurs. Therefore, when two events are independent, the rule for conditional probability takes a different form, as indicated in probability rule 7. If the events are independent, then the probability of E1 given E2 simplifies to the probability of E1 such that E2 has a probability greater than 0. Converse must also be true. We need to define the joint probability of two events in the discussion on addition of two events and in the discussion on conditional probability. We were able to find the probability of E1 and E2 simply by examining the joint relative frequency tables. However, we often need to find probability of E1 and E2 when we do not know the joint relative frequencies. When this is the case, we can use the multiplication rule for two events. As we saw before, we can also utilize a tree diagram when using the multiplication rule. In this case, we would simply multiply each branch by the previous branch to obtain the experimental outcome. If the two events of interest are independent, the imposed condition does not alter the probability, and the multiplication rule takes the form shown in probability rule 9. The joint probability of two independent events is simply the product of the probabilities of the two events. Rule 9 is the primary way that you can determine whether any two events are independent. If the product of the probabilities of the two events equals the joint probability, then the events are independent. As decision makers, you will often encounter situations that require you to assess probabilities for events of interest. Your assessment may be based on relative frequency or subjectivity. However, you may then come across new information that causes you to revise the probability assessment. For example, a medical doctor might assign an 80% chance that a patient has a particular disease. However, after seeing positive results from a lab test, he might increase his assessment to 95%. In these situations, you will need to find a way to formally incorporate the new information. One very useful tool for doing this is called Bayes' theorem, which is named for Reverend Thomas Bayes, who developed a special application of conditional probability in the 1700s. Letting event B be an event that is given to have occurred, the numerator can be formulated using the multiplication rule, and the denominator can be found by adding the probability of the k possible ways that event B can occur. This is Bayes' theorem, where all events are mutually exclusive and collectively exhaustive. One method that might make dealing with Bayes' theorem easier is to use a tabular approach. This method breaks the probabilities down into prior, conditional, joint, and finally revised probabilities. Suppose a drilling company has estimated a 40% chance of striking oil with their new well. A detailed test has been scheduled for more information. Historically, 60% of successful wells have had detailed tests, and 20% of unsuccessful wells have had detailed tests. Given that this well has been scheduled for a detailed test, what is the probability that the well will be successful? If we use Bayes' theorem, we see the revised probability has risen from the original estimate, so we see a greater chance of the well being successful. Go ahead and open Excel file Courtyard Survey, and let's answer the following questions. Since we are interested in 2 customers being selected, what is the probability that both customers will be on a business trip? To determine this, column J will be our interest, and I would begin by creating a pivot table. So column J will be were you, set values to count. In this case, 1 is business trip, so we have 27 out of 62 values. So to find 2 individuals, the first probability would simply be 27 divided by 62, and the second probability would be 1 value less. So it would be 26 divided by 61. Now for the second question, we want to determine the probability that a customer will be on a business trip or will experience a hotel problem during a stay at Courtyard. So in this case, we'll create another pivot table and add the were you column J to our rows and column I for any problems in columns. Again, we know 1 for rows here will be business, and in the columns labels, 1 will be problems, 2 will be no problems. So to determine the probability of business, we're going to take the 27 divided by our 62, and since we see the word or, we know that we're going to be adding and eliminating any double counts. So we'll take our 27 divided by 62. We'll also add the grand total of problems, since we want to determine the probability of a hotel problem, which would be our 14 divided by 62. And notice in the red here, we've double counted this 10, so we're going to remove the 10 from our overall probability. So we see there's a 0.5 chance of a customer being on a business trip or experiencing a hotel problem during a stay at the Courtyard. Here are 2 more questions that we could answer. So the first one is, what is the probability that a customer on business has an in-state area code phone number? So again, we'll use a pivot table to drag were you into rows and phone into columns. So to determine the probability of business and in-state area code, we'd go to the intersection of our business trip, which is 1, and our daytime phone number of 1, which would be our in-state. So we would simply take 2 divided by 62. So we see that there's a 0.032 probability that a customer on business has an in-state area code phone number. The second question asks, based on this data in the survey, can the Courtyard manager conclude that a customer's rating regarding staff attentiveness is independent of whether he or she is traveling on business, pleasure, or both? If a customer's rating is independent of the staff's attentiveness, we would expect the probability of business and pass to be the same as the probability of business that we found earlier. Again, here I would add the were you into the rows and attentive to columns. Again, the probability of business is simply the 22 divided by 62, and to find the probability of business and pass, we use probability rule 9, multiplication rule for independent events. The result would be 52 divided by our 62 times 27 divided by 62, which we can see is not equal to the probability of business. Therefore, they are not independent of each other. Here are 3 more questions. First one, of 2 customers selected, what is the probability that neither will be on a business trip? The easiest way to determine this is to simply do the complement rule. Previously, we determined the probability of both being on business is 0.1856. We would simply take 1 minus that to determine the probability that neither will be on business. For the next question, what is the probability that a customer will be on a business trip or will not experience a hotel problem during a stay at the Courtyard? To determine the probability that a customer will be on business trip or will not experience a hotel problem means we're going to add and eliminate any double counting. So to begin with, we'll take our 27 divided by 62 plus 48 divided by 62 minus our double counted 17 out of the 62. So we see here there's a pretty high probability that a customer will be on a business trip or will not experience a hotel problem during a stay at the Courtyard. And our final question is, what is the probability that a customer on a pleasure trip has an in-state area code phone number? So to determine this, it would be the intersection of our pleasure trip, which is number 2 on the row labels, and number 1 for in-state. So it would be the 2 divided by 62.